Okay, so now let's actually use all this stuff for practical things, for example, in simulations. So one thing I can use the MinPos, for example, is to create artificial forces based on the surface of something. So something like a magnet. And in POPs, this would look like this. I have here points that are an initial state. So they come in from the POP object under initial geometry. So I'm not constantly emitting new points, but those are a limited amount of points. And then this magnet here is currently just a static object, so it can collide with the points. But currently nothing else happens. There's no gravity. And I can use a POP wrangler for this. And just like that would also work a geometry wrangle. Both when they are set to points do exactly the same thing. Geometry wrangle is interesting later on when we work with different kind of geometry, like so-called constraints. But for now, let's keep it simple. And a simple POP wrangle allows me to use vex to create stuff. And one thing I can actually do is I can create my own force vector. And this is something I don't think we ever did in the POPs chapter, but this is what we do now. So the force attribute is basically like a force. One tip already though, you have to put this before all the other forces, otherwise it will overwrite them. So this is kind of the starting force, let's say, and we can calculate, since it's a vector, what we calculate basically is the direction the points will be accelerate towards. And this is important to understand for this concept. So the direction we need to calculate is the vector from the current point to the closest point of the surface if we want to have a magnet, of course. So as usual, so first we calculate the second position, and I do this with a MinPos. So now one thing that is special here, since this is a POP wrangle and doesn't have any inputs, we can't just read out geometry 1. Well, we can, but it's not based on the inputs up here, but on the inputs in the tab here. And this is very important when you use a POP wrangle with vex, that you have to define your own inputs. Now I keep using 1, even though I could use 0, because the inputs start again from 0 to 1 to 2 and 3. So even though it's called input 1, this will be readable with 0. And this is why, kind of to keep it consistent, I prefer to use input 2. And here I can now say what this should be. And since I already put my magnet into the second input here, it makes sense to also use this as a second input for this one. And in general, I try to use it as a second input. So the MinPos of what, yes, relative to the current position and based on the second input, which is the magnet. So to calculate the direction from the current point, we learned we have to subtract one from the other. And honestly, I never remember what the order is, so I do it probably wrong on purpose here. So I say current position minus position 2, and what will happen is, of course I was wrong, but as you can see, first, it works. B, the direction seems to be correct if I look at it in simplified terms. And also what it shows, if I wanted to do this, of course I can create a pushing effect as well. But we don't want to do this, so let's turn this around to this order, and now it should move towards it. And this actually works, and it's kind of fascinating what's happening now. What is happening here? Well, it's actually quite simple, and this is something we already saw with the POP attract video. Whenever you have something that accelerates towards something, then it's the nature actually of things to overshoot. And this is not just a Houdini thing, by the way. This is how the universe works, because this is why planets are actually rotating around a star, because they're accelerated towards it and then are kind of shooting over it, and the magnetism or the gravity pulls it back, and this creates a circular movement over time, which is exactly what we're seeing here. So this is actually how solar systems work. Pretty annoying nonetheless. So what can we do here? What usually works is when you just say, okay, they should not all accelerate in the same amount. Well, first of all, it's actually not accelerating by the same amount. Currently, the length of the vectors, and we can visualize this. We can actually visualize the force attribute that we just set, which we will, of course, also find in the geometry overview here. If we type in force, there it is. And as you can see, the further away it is, the longer the vector is, so the stronger the force. To bring this to always the same strength, we can just normalize it, of course. So we put a normalize around the vector we just created, and now it doesn't really seem like it, to be fair, but they all have the same length. Maybe let's quickly change the visualizer to an extent. But this will not actually solve the problem. This is just something that is nice to have, because this way it's a bit more, predictable, but it still overshoots. What can help here is, well, first of all, let's control it by the distance. And the idea here is the closer the point gets to the magnet, the stronger the force gets, and then the overshooting, let's say, is less likely. It will still happen, but it's not as strong anymore. So how can we do this? We just multiply the whole thing. We can actually do this in the next line. We multiply it with something, and that could be a remapped, let's call it remapped dist. So first of all, we have to calculate the distance. So let's actually do this. So the distance, of course, between my current position and the goal position, so to say. And the remapped dist would then use that. Oops, not fit, it's a float. But it uses the fit to take that distance and remap it. And this is now, of course, up to you, because this defines, okay, how far away does it have to be to have no effect, and how close does it have to be to have the highest effect. What I will do here is I say, okay, 0 will be the strongest. And based on my case, let's hard code this for now. Maybe, I don't know, 3 meters sounds about right. And the logic here is simply the closest it is, the strongest it will be. So this will be 1. And therefore, when it's furthest away, the result will be 0. So because this will be multiplied. So in other words, if it's 3 meters away, then there will be no force. If it's exactly on top, the force will be 100%. So this will just change the behavior a little bit like this. But again, it doesn't change our behavior yet, because the force basically is still too low. So I add a multiplier on top of this to kind of define what is the max strength, which, yes, if you think you could have done this here as well, replacing the 1, you're right. I prefer to have this always normalized. So this now I can, I don't know, crank up to 6 or something. And then hopefully we should see that the points, yeah, okay, actually the whole effect just got stronger. So what is the next thing? As I told you, this is not enough, but it's a good first measurement. What actually helps here when you have overshooting is a pop drag, because a pop drag basically makes sure that there's always a little bit of a slowdown happening all the time. So like an air resistance. And if you combine those, you can see it's still kind of, varying and moving and all that, but it's in combination, this usually stabilizes the system. And yeah, this is pretty much our effect, and you can see it works. And the interesting thing about this is not so much that points are attracted in a certain direction, but that they're actually attracted based on the shape of something. And this is what makes it so interesting. Now, of course, you can extend this or change this by many things. So, for example, we could, on top of all this, add a randomizer. This time I can use the PT num because they're not sourced, so the point number isn't changing. So this is safe in this case. And now every point has a slightly different behavior that can add a little bit more, organic behavior to it. The only problem with that is, of course, that some strength will be too low. So let's make sure that we fit that rand with an O tube to save some typing time, precious typing time, and say, okay, there will be a random number between 0.5 and 1, or actually 1.5, why not? And then it looks like this, which gives it a bit more variation. And then, of course, and this is the last thing I will do with this, I can, of course, also add a pop force to add a little bit more variation to the whole thing. Well, okay, to be fair, this now happens to everything. Maybe what we can do here is we also set an attribute if the, how can we do this? Let's say if, actually, we could read out the force for this. So we could say the group is only happening when the, that's the dot drag here. When the force actually no, just at force, is higher than 0, then the pop force will trigger. That's one way I think could work. Yeah, that's an easy way of doing this. Only the points that already have a force will get a pop force on top. Okay, here's another example. Actually, not doing it in pops, but do it in Vellum. And if you haven't seen Vellum yet, so if this if you're watching this before you watch Vellum, please just ignore this and come back later. This chapter, as I said in the beginning, is not meant to be, watched completely after pops before you move on. This is something to come back to or do it later. So this is why I'm jumping a little bit in the simulation types. So here I show a Vellum example, and I will not explain every detail here. What I have is just copied a couple of lines with enough subdivisions so that we have enough deformation. And this I turned into a hair. You can also do it into a string. And important is that the first point of every line gets a pin attribute. And this pin attribute is then used to pin that thing in space with a pin to animation. Oh yeah, and I also lowered because it's supposed to be underwater. It's kind of an anemone behavior. I lowered the gravity to something really small. And what we get then, in combination with a moving sphere that is animated, is for now just a couple of underwater hairs, let's call it, that react to the sphere when it moves through. There you have it. Nothing special. Now to make this more special, we first of all add a little bit of a pop force. I already had this prepared, nothing special, with a little bit of an upwards movement, again to kind of simulate the idea that this is underwater, okay? But still, this is just a collision. There's nothing where we control the forces ourselves. So let's do this now. And we use a pop wrangle here again, because of course, Vellum simulation is point-based. And we can do the same thing again. It's really straightforward now. So of course, we find the point on the sphere, which would be a min-pos. And I have to be careful again to use the right inputs. So where do I have my sphere? Well, I can't directly use the inputs here because the way the Vellum DOP-SOP wrapper is built, it has multiple layers. So this will not work. But what I can do instead is I use a SOP path, and I have prepared this here and I called it out sphere. So I have to find this in my scene, and there it is. So it's an absolute path, basically. And now I calculate the direction, or this time I put it into an internal variable. And this would be, and this time I think I do it right, the P2 minus my current position, and let's already normalize this. And then I put this into a force. Let's see what happens. Oh yes. That seems to work, but here's the problem. Be very careful. In some cases, this can be a way too strong force that comes out of this, depending on your scale and everything. So let's make sure we add a controller for this by a simple strength multiplier. And actually I already saw that we have to be really careful with this. As you can see, even 0.1 is really strong. So maybe let's try 0.001. Yeah, and here you can see, basically we could stop here. This is what we needed. Now we just have to extend this, but it already works. Once again, this here is a distance based. So let's calculate the distance. Easy for us at this point. We have a distance, and now let's remap that distance. And this time I put it on controllers. So I have an input minimum distance, or actually it's called minimum distance. I have a maximum distance, and this will be mapped to 0 and 1. But how again? Well, the closer it is, the stronger it should be, and the further away, then it will turn off at some point. So this is the way around we need it. And this then will be just a multiplier because it's between 0 and 1. And now we just have to make sure that we find good numbers. So let's keep the minimum distance at 1. And let's say 1 meter for the maximum effect. So everything further away from a meter will not be affected. Let's see how this works. Yeah, that looks good. Yeah, and then depending on how strong you want this effect to be, maybe we do make it stronger again. But you can see it works. It feels like the anemones based on the distance react to our, let's call it magnet again. And if it's further away, then they kind of forget what they were doing and have no no force applied to them anymore. One thing I already mentioned, be careful with the order here. So let me quickly, just for fun, change the order of the pop force and the pop wrangle. So as you can see here, our vex still works, but the pop force seems to be ignored. And the reason is that we, by this order, overwrite the force that was set here before. So always make sure to put your vex code in the beginning when you write the force directly. And now we have both on top of each other. Okay, so this is how you can actually use the min-pos function and the distance function to set the force. You can see it's pretty powerful because you can create your own magnet force, basically. I hope this is helpful. Thanks very much and see you later. Cheers.